All right. So to do fraction subtraction, we need to identify which model we're using. And you can use either one for most problems. You could use takeaway, you could use comparison. Let's go for takeaway. And then we would make a note and count what's left. And then we have to take it away, we have to report an answer. So that's what subtraction means. What is a fraction? So we also need a model for fractions. And the model we used in the addition stuff was equal parts of a whole area. So let's pick an example to work with. Let's say we want to do 1/2 minus 1/3. So under this particular model, we need to take 1/3 away from 1/2. So we need to be able to see the 1/2 to do that. So let's start with the color strips. We've got the digital version here. Let's see, here we go, clear. So let's use the dark green 6 as our whole. And we want to take away from 1/2, we want to take away 1/3. So maybe we'll line them up like that. And so we want to draw this to the best of our ability or get the toys out. Okay, that's what we have to work with. So can I directly take away 1/3 from 1/2? No, I can't directly take it away. Now, if we were doing a comparison, that's a little different, but still, even with the comparison, I got to do something else. 1/3 and 1/2 aren't directly comparable. Okay, so what other shape could help us compare here? A white one, yeah. I need to take the whites and use those. So I'm going to throw the whites in here. So I need 3 whites to make the light green, and I only need 2 whites to make the red. All right, so let's try this again. All right, so our original goal here was 1/2 minus 1/3, or from 1/2, take 1/3. And that doesn't work directly, so we kind of rewrote the problem. So what are we calling 1/2 instead now? 3/6. Yeah. So now we've got 3/6 minus 2/6. So this now becomes pretty easy. So from 3/6, take 2/6. Now can we easily identify what's left? There should be 1/6 left. We should make that as a statement. There it is, 1/6 Now, as far as the mechanics of kind of an algorithm, which we need to approach next after we do a few more examples for addition and subtraction, we had 1/2 minus 1/3. And based on the toys, we rewrote that as 3/6 minus 2/6. And remember, the 6, the denominators, they're just a description. What do the numerators mean? Yeah, numerators are count. Yeah. So these up here are count. So from 2, we take 3, that leaves 1, and 6 was the description. So one thing we get from the toys is, if we have a common denominator, we just subtract the numerators. So that's an important thing to note. And it's not much different doing this with the pattern blocks. They're just a different shape and feel, but the process is pretty much the same. Let me bring up the pattern block toys. So to use the pattern blocks, I have to identify what a hole is. And then I got to figure out what is 1/3 of that hole. And so we played around before. Showing that this shape is 1/3 of a hole. Let's get over there. All right, so there's my 1/3 of a hole. We know these guys are, let's see, what else do we want? I forgot which problem we're on. One half minus 1/3. There we go. And then I have 1/2. All right, so what is 1/2 minus 1/3? So what do we have to do to make this work? Yeah, we got to break out the triangles. There's no other way to do it. So we have to take a bunch of triangles out. And these aren't as much fun as the physical ones. Come here. There you go. So just like working with the little whites, we can use the triangles here as kind of our lowest common denominator to come up with an answer. So pretty similar. Just a slightly different drawing. Let's draw it with the cakes next. When I use the cakes, I think kind of like with the addition, I'm going to view subtraction as a comparison. And with a comparison, we're usually trying to ask a question like, how much more is one than another? And I want to show what does 1/2 minus 1/3 look like as a comparison. So draw a square for 1/2, make your cut, and shade part of it. And then similarly make an equal sized whole square to the best of your ability for a third. Cut that the other way, vertical versus horizontal, whichever you didn't do first, and shade again. The middle one this time. Are each of these pieces the same size, directly comparable? They're not, right? So we have to recut. So let's go do that next. So we get the halves cut in thirds and thirds cut in half. So now we've redefined the problem. What is the problem now? I have 3 pieces minus 2 pieces, and what is each of those pieces?
6.
Yeah. So a couple ways to write it. We could just write 3 minus 2, big fraction bar with 6 underneath. So you'll see it written that way in books sometimes in exercises, so we get the answer of 1/6. That's how they're different. So the question here is a comparison. How much more is one than the other? So can you write a sentence talking about the difference between 1/2 and 1/3? With the question, how much more is one than the other? So you're trying to answer that question. Write your best answer to that question as a sentence.
So we have to put how much more is from 1/2 to 1/3, not 3/6 and 2/6.
Yeah, starting with the original fractions. Yeah. 1/2 is more, right? How much more is 1/2 than 1/3? There's a lot of ways to word that. Come up with your best idea. Here's one shot at it. 1/2 is 1/6 more than 1/3. And based on our comparison. Difference between them is 1/6. Can anyone think of another way to word that?
So I did the same thing, but at the end I put 1/6 is a whole number. Would that not be a good thing to put?
Read your whole sentence to me.
So I just did 1/2 is 1/6 bigger than 1/3, 1/6 is a whole number.
I get what you're saying, but I don't think you need the 1/6 as a whole number.
You don't? Okay, that's what I wasn't sure of.
When
If
there's 6
the-
pieces in a whole, I think, is that what you're trying to say there?
Yeah, like
Okay.
to explain that that's the whole number.
Yeah, I think the picture shows that. I don't think we need to state it, but I guess I would clarify it. Not when 1/6 is a whole. When where did you write when 6 is a whole number?
When 6 is a whole number.
Yeah, when there's 6 equal parts in a whole would be the better way to state that.
Okay.
Yeah. The other way we could write this, we could say the difference between 1/2 and 1/3 is 1/6. And we talked about the word difference before when we were talking about the comparison model. The answer of a subtraction problem is called the difference. 1/6 is the difference.
Is this sort of like what the problem that I wrote with it last week was? What is in the middle of 1/6 and 1/7?
What's in the middle that's a whole different
Or is it
question.
different?
Yeah, that's a whole different question than this. Yeah, this is how do we come up with, if we know what subtraction means and we know what a fraction is, how do we figure out how do we subtract? And that's what we're trying to do here. Now there's going to come a point where we're not going to want to draw these pictures. Okay, so for example, I do not want to draw 7/20 minus 5/18. We don't have color strips that are big enough to draw this. The pattern blocks would be too crazy and difficult to draw it. And even a cake for this is going to be hard to look at. Right? So we've got to move beyond to come up with some other methods. And so we're going to try and come beyond. So we need an algorithm. And I know you guys already know algorithms, but we're just developing it slowly. We don't want to model this. Model means show me physically what it means. And once you get beyond like 6 as the denominator, it's too much of a pain to draw. The toys get too hard to deal with. There's too many pieces. They're hard to count. We need an algorithm. So the first algorithm that comes from the drawings that we did with the cakes, so we'll come back to this. Is the idea of cutting each like the other. So for example, 1/2 minus 1/3. So what had to happen here is the halves had to be cut in thirds because that third was down there. And the thirds had to be cut into halves because the halves were on the other fraction, that other description. We had to make them share descriptions. So that one piece got cut into 3. And this one piece here got cut into 2. And these 3 holes got cut. These 3 pieces over here got cut. Those 2 pieces over here got cut. What happened when we put the 3 and the 2 together as a whole? We got 6. 3 times 2 is 6. So the cutting leads to this algorithm right here. This is called the arrow algorithm for fractions. This particular algorithm works for addition or subtraction. Multiplication and division are different. It always works. It's the quickest way to get an answer, but it doesn't necessarily give you the simplest answer, which we'll see in just a second. So what was I trying to do with these fractions in the first place? These two? Subtract, right? So I got to remind myself I'm subtracting, so I usually do that up there. So we do this cross multiply and multiply across the bottom, and then we just put it all together by saying 3 minus 2 is 1, 6 has to be in the bottom. So let's revisit the arrow algorithm on another problem we did earlier. We did 1/3 plus 1/6 was one of the problems we did with toys. So if I look at the arrow algorithm on this right here, usually what I do first is cross multiply. 6 times 1 is 6. 3 times 1 is 3. Remind myself I'm adding versus subtracting. And then the denominator just comes by multiplying the denominators. That's that idea of cut each cake like the other. So my denominator here is 18. What's 6 plus 3?
9.
9. And then it has to be 18ths. All right, so that's the arrow algorithm. There's another algorithm which is taught in schools that most people do. So let's try this again, called the Lcm algorithm. So we'll just look at a brief example of it, and we'll do more details with it in a little bit. There's a process for guessing at a smaller denominator. So given your experiences, I bet you guys can say, hey, I think blank would be a good denominator. What do you think would be a good denominator by looking? It's because 3 goes into 6, right? So first step is kind of decide what should the lowest common multiple of the denominators be, and we say, hey, we believe it's 6. Okay. LCM is a whole nother topic we looked at last chapter. So step 1 is coming up with that LCM. Step 2 is to modify the fractions. And here we only have to modify by multiplying 2 into the top and bottom layer. And then kids are usually told to rewrite it. This is now 2/6 plus 1/6, which is equal to 3/6. Now, even though we found the smallest possible denominator, there's no way to do this problem with a denominator smaller than 6. What do I still have to do here? I still have to reduce. So this one is going to reduce down to 1/2. Just like this one up here is going to reduce down to 1/2 eventually. So as we play around with addition and subtraction algorithms, we get to look at pros and cons of either algorithm. What's the benefit of using the arrow algorithm over the LCM algorithm? All right, so let us break down the LCM and arrow algorithms on this problem right here. So we have two options here. We can do the arrow algorithm. Or we could do the LCM algorithm. So what I'd like you to do is try this either way. Try to use the arrows I drew a minute ago, or think back how you were trained to do it with the LCM algorithm. So pick one way, go for it, get an answer.
This is not the
Oh,
It's like
what? Oh my God. We got cheated. There's only one short one in the whole thing? Or is there
no,
one long one?
that's the long
We
one.
just happen to have a long one. I'm going to take that away. I'm in trouble. So pick an algorithm, arrow or LCD, come up with an answer, resist using your calculator if possible. I know it's hard.
So, I was using it to multiply,
That's okay.
not to.
Calculators are wonderful, beautiful tools. We should use them. $18 times 7 in my head is a little tricky, but doable. All right, so I'm going to try the arrow algorithm first. Everyone got one shot at an answer? Okay, so let's see if we get our answers right. All right, so the arrow algorithm, I got to do my cross multiplying and my side multiply there. So let's see, don't help me yet. 7 times 18 is 70 plus 56, which is 126.
Mm-hmm.
All right, 126 there. 20 times 5 is 100. So that means I have 126 minus 100. And I'm in the habit of rewriting the addition or subtraction symbol so I don't forget and actually subtract when I should add or add when I should subtract. So I recommend that. So 126 minus 100 is going to give me 26. Out of 20 times 18 is 360. And that's an answer, but I noticed they're both even, so I'm dying to reduce. So I'm thinking, all right, I can divide those by 2 to get a better answer. So that would be 13 over 180. and 13 does not go into 180. 13 is prime, so I think that's the simplest answer, if I didn't screw anything up. That wasn't so bad. Okay, 7/20 minus 5/18. I'm going to try the LCM algorithm.
With those numbers that we got, the answers, it has nothing to do with like that, but you have a full circle and then literally half a circle. So 316 makes it.
Oh, the degrees you're thinking about?
Yeah.
Yeah. Okay, so to use the LCM algorithm, I have to first find the lowest common multiple of 20 and 18. And we had at least two ways to do that. One way is to list out a whole bunch of multiples of 20. Another is to list a whole bunch of multiples of 18 and find the first match. That's a long list. It's doable. What was our other technique? My favorite. Well, we got it. Well, that was the fraction. That was the arrow one. So all I want to do is find what's the smallest number that they both go into. And the process we use is to make a factor tree on each of them. So I'd say, okay, what are the prime factors of 20? So prime factorization turns out is the most efficient method. All right, so 20 is 2 times 10, which is 2 times 5. So 20 is 2 times 2 times 5. And then I do that for 18. 18 is 2 times 9, which is 3 times 3. So 18 is 2 times 3 times 3. And we talked more before about writing them with exponents. So I could also rewrite them and say this is 2 squared times 5, and this one is 2 times 3 squared.
Shouldn't the exponent come before the 2? The 3 shouldn't that come before 2? Because of a higher power.
Well, I'm just writing down what they are. I'm not coming up with the lowest common multiple yet. That's my next step. So usually when we write the prime factorization, we write the primes in order from smallest to largest with their powers. So all I'm saying right now is 20 is equal to 2 squared times 5, and 18 is 2 times 3 squared. The next thing I need to do is I need to put those together and come up with the lowest common multiple. And we had 2 techniques for doing that here. One technique was just to say, hey, 20 has to have a 2 squared times 5. And then 18, what does 18 need? Does 18 need any more 2's than we have written down already? Nope, we just need the 3 squared. So this combination of factors right there is the lowest common multiple, so now I have to multiply all those out. So if I take one of these 2 times 5, that gives me a 10. The other 2 times 9 is 18. 10 times 18 is 180. But I had to do all that work just to come up with a denominator. Next, I have to figure out, well, how many times does 20 go into 180? So this was step 1. Over here, I'm going to put step 2. 2 is to say 180 divided by 20 is what? 9. And then 180 divided by 18 is 10. So that tells me right there that up above I need to multiply by 9 here and here. And I got to multiply by 10 here and here. Question? Okay. So we have to find out what's the smallest denominator we can use, and then we have to figure out what do we multiply each of the old denominators by. So how many times does 20 go into 180? 9 times, multiply top and bottom by 9. How many times does 18 go into 180? 10 times, multiply top and bottom by 10. So then I can rewrite these as 7 times 9, which is 63 on a good day, and 5 times 10 is 50, over a common denominator of 180. And some books will just jump right to this, writing the denominator once we find it. Others will write it as 63 over 180 minus 50 over 180. I like less writing, but it depends on the book you use. 63 minus 50 is 13 over 180. That was a lot of work. This is what we teach in the elementary school. Okay, look at all that work. Look at that work. This one makes me happy. Elsie is like, oh, when I turn the pages, thank you. I can see this relief wash over you there. So I love all kinds of math. I like complicated processes. I think they're fun, but most people aren't like me. They like other ways to do it. I like drawing those cakes. Those are fun. Slicing them each way, it works. It's nice. This is the result of slicing. Now, drawing this picture is a bit problematic, but this whole cross-multiply idea, that's not too bad. Right? So, but there are pros and cons to each of these. You have bigger numbers to deal with here, because I had to take 20 times 18. 360 is a lot bigger than 180. Well, it's twice as big, but it feels a lot bigger. On the other hand, this right here was a lot of work, finding what is the lowest common multiple. Sometimes it's obvious, we just look at the numbers. But do we all see the same things?
No.
Right? We don't all see the same things. Did anyone just look at those two numbers, 20 and 18, and think, oh yeah, 180 is the smallest number? I didn't, right? And I see these numbers all the time. So I'm not saying the LCM algorithm is bad. It is a great algorithm. It gives you the smallest denominator possible to get them added or subtracted. But you still have to reduce sometimes. Did we have to reduce at the end of this problem? No. So people who don't like reducing, hey, you don't have to reduce as much. You still have to reduce sometimes. The answer is, yeah, you do still have to reduce sometimes, even with the smallest possible denominator. All right, so you got this example written down right here? So here's what I'd like you to do. Look at your notes. Look at the example I have on the board. List the steps that one must go through. So suppose a parent calls you, hey, you're going to be a teacher. Me and my kid were really struggling with fraction addition. Can you write down the steps we're supposed to use? I'd like you to try and do that right now. Give it a shot.
For the LCM?
Step one, yeah, for the LCM. Forget about the arrow for now. Write down what you think based on our work right here. So this isn't a really easy problem, but it's not a really hard problem either, right? It's kind of intermediate. It's hard enough that all the steps are living here that we need to follow. Except one, there's one step kind of missing. We'll identify that. So just do your best. We'll fix it, don't worry. I'll pause the recording here. The steps are here.